After studying this module, you shall be able to know the application of non-parametric tests, learn the Kruskal Wallis test, concept, applications and numerical, and learn the Friedman two-way ANOVA. Introduction. One knows that not all the variables in psychological research are quantifiable. Many research involve variables that can be measured in qualitative scales only. Let us take an example. A researcher is interested in knowing if the accuracy in response is dependent upon the decibel of sound in the vicinity. The number of times subjects make mistakes in the clerical speed inaccuracy test was recorded with increasing decibels of sound at 3 levels: high, very high and unbearable. Subjects were chosen from the student population of University of Delhi. The data here is in ordinal scale of measurement. So, application of parametric statistical techniques is questionable. The non-adherence to parametric assumptions in data paves the way for usage of non-parametric statistical techniques in research. Non-parametric tests in single factor designs. Single factor designs are used to study the effect of one factor, independent variable, on the dependent variable. When a researcher tries to study the effect of a variable, it is called independent variable or factor in the research design. The investigator studies the effect of the factor by experimentally manipulating 3 or more conditions or levels from it. When the data is unable to support the assumptions of parametric tests, the obvious choice is the non-parametric statistical methods. Analysis of variance is a highly robust test when its assumptions are met, but under conditions when distribution of scores is non-normal, homogeneity of variance is lacking and measures are nominal or interval levels, then ANOVA is not suited. So, when the data shows deviations from normality, that is, it shows high or low kurtosis or skewness, then ANOVA values may be inflated or deflated. That is, in a non-normal data, deviations from normalcy, whether skewness or kurtosis, would lead to a distorted value of ANOVA, and applications of ANOVA in such circumstances is not permissible. Homogeneity of variances across the different groups of the research design should be observed. The ANOVA may not be an appropriate measure. That is, only when the homogeneity of variance is there across the groups, ANOVA would be suitable. If we don't observe homogeneity of variance across the different groups, then ANOVA may not be a suitable method to be applied. The test or the data is in the lower scales of measurement, that is, the dependent variable is not continuous, or in qualitative scales, ANOVA cannot be applied at all. That is, the data needs to be in higher orders of measurement whenever ANOVA has to be applied. In such conditions, the non-parametric tests come to the researcher's rescue. So, when the data violates the assumptions and ANOVA cannot be applied to check the significance of differences between the groups owing to the ordinal measurement of the data, non-parametric tests prove to be very useful. As non-parametric tests are relatively assumption free and cater to small sample size, they prove to be useful and powerful in such data. Let us have a look at the figure. There are two experimental variables with treatment A and treatment B. The control variables are that they are controlled at level 1 and level 2. This is the arrangement of the factorial research design that is suitable for the application of ANOVA. Let us look into the two types of non-parametric alternatives to ANOVA, that is the Kruskal Wallis test and the Friedman's ANOVA. Let us begin with the first one, that is the between subjects factorial design, where the Kruskal Wallis test is applicable. The concept of Kruskal Wallis test. The Kruskal Wallis one-way analysis of variance by ranks is named after William Kruskal and W. Allen Wallis. It is a non-parametric method for testing whether samples originate from the same population. It is used for comparing two or more samples that are independent and that may have different sample sizes, and extends the Mann-Whitney U-test to more than two groups. The parametric equivalent of Kruskal Wallis test is the one-way analysis of variance, and when rejecting the null hypothesis of the Kruskal Wallis test, then at least one sample stochastically dominates at least one other sample. The test does not identify where this stochastic dominance occurs or for how many pairs of group stochastic dominance or analysis is obtained. The Dunn's test would help analyze the specific sample pair for stochastic dominance. Since it is a non-parametric method, the Kruskal Wallis test does not assume a normal distribution of the residuals, unlike the analogous one-way analysis of variance. If the researcher can make the more stringent assumptions of an identically shaped and scale distribution for all groups except for any differences in medians, then the null hypothesis is that the medians of all groups are equal, and the alternative hypothesis is that at least one population median of one group is different from the population median of at least one other group. The function of Kruskal Wallis test. Kruskal Wallis test is a very useful non-parametric test that helps in deciding if the number of samples chosen for research are from different or same population. The test helps in deciding if the variance shown by the samples is attributable to the genuine differences between them or just expected random variations that have cropped up because of sampling errors. The Kruskal Wallis test based upon the rank data. It is a discrete ordinal dependent variable is used in the test. A continuous variable can be studied, however. The observed continuous scores have to be converted to ranks in analysis. The subjects in the groups being compared and their scores are not related in Kruskal Wallis test, or to put this in other words, this is referred to as between group designs. The null and alternative hypothesis that the Kruskal Wallis technique tests are HO is phi 1 equal to phi 2 equal to phi 3, and the alternative hypothesis is that phi 1 is not equal to phi 2, where phi is the population median. Although the test is a non-parametric test and is considered assumption free, it is important to know that the observations are independent and there is some degree of continuity of the variable used. the application of Kruskal Wallis test on research data using a numerical example. When the research design is between subjects with more than 2 levels of the independent variable and the requirement of the parametric ANOVA are not met, then the data is suitable for its non-parametric equivalent, the Kruskal Wallis test. Let us demonstrate this with the help of a research data. A researcher wishes to study if the gender of the subject has any bearings on the assessments given to his work by the experts. The experts were asked to grade the articles written on a topic by groups under 3 categories: male, female and unspecified, that is, not given any indication of gender. 24 school teachers were taken as experts and they were each given the same article that was marked either by male or female or unspecified, that is, not given any indication on gender. The grading was to be done on a numerical grade from 1 to 9. The data sheet is presented below. Notice that the grades have been converted into ranks. We find the gender of the author: male, female, neutral and male, and the grades have been converted to ranks. The total of the ranks is also given in the row at the bottom. The null hypothesis is that the medians for 3 conditions do not differ. That is, phi 1 is equal to phi 2 is equal to phi 3. The alternative hypothesis, of course, is phi 1 not equal to phi 2 not equal to phi 3. The Kruskal Wallis statistic is calculated as given in the equation h equal to 12 upon nx into n plus 1 multiplied with sum of r square upon n minus 3 into n plus 1, where capital N is the overall number of participants, R is the rank, N is the number of participants in the group, like in this case it is 8. After the application of the formula and substituting the values of the given numerical example in the equation that is to be used for calculation of H, the Kruskal Wallis statistic, it was found that the value of the Kruskal Wallis statistic H is equal to 2.08625. Now, to test the significance, we must notice that H is distributed like chi-square with degrees of freedom of 1 minus k, where k is the number of levels of the independent variable, which in this case is df is equal to 3 minus 1, that is equal to 2 in this case. Now, to check for the significance of the Kruskal Wallis statistic H, we look up the chi-square distribution and we will find that the probability P lies between 0.5 and 0.3. This means that there is insufficient evidence to reject the null hypothesis. So, we can conclude that the experts did not differ in grading the articles on the basis of their knowledge of the power and Kruskal Wallis test. The power of a non-parametric test is given in terms of power efficiency of their parametric counterparts. If the assumptions of parametric ANOVA are not met, then Kruskal Wallis test may have more power than its parametric equivalent, that is ANOVA. Using IBM SPSS 20 for the Kruskal Wallis test. The research data consists of 60 multiple sclerosis patients which were randomly assigned to the three treatment conditions. The participants in the first condition receive a low electric stimulation, the second group receives a placebo, and the third group receives a high electric stimulation. The dependent variable in the pain is the pain improvement as measured by the McGill Pain Questionnaire. The obtained data is fed to the data sheet under the relevant titles, and the following IBM SPSS 20 commands can be given for the Kruskal Wallis test. Click Analyze, go to Click Non-Parametric Tests, click Legacy Dialogues, then click Independent Samples, click over Pain Improvement under Test Variable, under Test Variable List, and Electric Stimulation under Grouping Variable. Go to Click on Define Range, type a 1 besides minimum and a 3 besides maximum, and click Continue. Then click on Kruskal Wallis H under Test Type. Click on the Options button, go to check the descriptive box, and then Continue, and then OK. The results would be generated. Save the generated output as Kruskal Wallis results. The within subjects factorial design, Friedman two-way ANOVA. The concept of Friedman ANOVA. The Friedman test is a non-parametric statistical test developed by the US economist Milton Friedman. Similar to the parametric repeated measures ANOVA, it is used to detect differences in treatments across multiple test attempts. The procedure involves ranking each row or block together, then considering the value of ranks by columns applicable to complete block designs. It is thus a special case of Durbin test. The classic examples of use are: n wine judges each rate k different kinds of wines. Are any wines ranked consistently higher or lower than the others? N wines are each rated by k different judges. Are the judges' ratings consistent with each other? N welders each use k welding torches and the ensuing welds were rated on quality. Do any of the torches produce consistently better or worse results? The Friedman test is used for one-way repeated measure analysis of variance by ranks. In its use of ranks, it is similar to Kruskal Wallis one-way analysis of variance by ranks. If the research design is within subjects and the independent variable has more than 2 levels, the parametric ANOVA is an obvious choice for the statistical tests. In those cases where the assumptions of the parametric ANOVA are not met and the levels of measurement is at least ordinal, Friedman ANOVA is an appropriate choice for the researcher. As the Friedman ANOVA is a non-parametric test, it is relatively free of assumptions, except that the data has to be in at least an ordinal scale of measurement. The researcher would like to study if the familiarity between people increased with increasing face-to-face exposures. A group of subjects is taken and exposed for 5 minutes to each other without any verbal communication. After that, response to a list of questions about the exposed member is taken. The repeated exposures, say about 5 more, after appropriate time intervals to each other followed by a set of questions about the observed person yields the data. The data obtained thus is suitable to non-parametric test as parametric assumption of continuous data are flouted. The functions of Friedman ANOVA. The Friedman ANOVA is used when the data from k matched samples are at least in ordinal scale. The null hypothesis tested is that the k samples have been drawn from the same population. The sample size is same as the samples have been matched. Purpose of Friedman ANOVA is to compare mean rank differences among two or more groups with related scores. There is only one independent variable used in Friedman ANOVA. The discrete ordinal dependent variable is used in this test. Continuous dependent variables can be used, but the observed continuous scores are converted to ranks in the test. The scores are related to each other, so it follows the within group statistical design. The degrees of freedom for Friedman ANOVA is 1 less than the number of samples, that is k minus 1 if k is the number of samples taken for the study. The Friedman ANOVA is a non-parametric statistical test and is distribution free. Thus, normally followed assumption of normality and homogeneity of variance of parametric tests do not fit here. It is important that observations are independent and ordinal scale is at least followed. The applications of Friedman ANOVA using a numerical example. A researcher plans a study to see whether a group of students rate a course differently if they spend more time on it. A group of students was made to join undergraduate course in psychology. They were asked to rate the course on a 7-point scale, ranging from highly disliked to highly liked. This was done after each term. The following data was obtained and subjected to Friedman ANOVA as compliance to parametric assumptions is violated. The table gives the data obtained for the numerical. The subjects are 7 and they have ranked the subject according to their choice, and the grades have been converted into ranks. The formula for calculation of Friedman ANOVA is chi-square Friedman. The subscripted f is designate for Friedman's ANOVA is equal to 12 divided by n multiplied with k multiplied with k plus 1, the whole multiplied with sigma r square minus 3 into sample size n multiplied with k plus 1, where capital N is the sample size, k is the number of levels of independent variable, r is the rankings given to the observations, and using the formula and substituting the values obtained from the data, we find the value of Friedman ANOVA turns out to be 4.07143 for the available data. The critical values of the statistic can be seen from the relevant table. The values are based on the sample size and the levels of independent variables. With large sample size, the distribution resembles a chi-square distribution only. In this case, the degree of freedom is equal to 2 by application of the formula k minus 1 equal to degree of freedom, whereas k is the number of levels. We find that the degrees of freedom for the current example is 2. Now, with chi-square Friedman turning out to be 5.429, the probability 0.05 and the sample size equal to 7, one can say there is not a significant difference in the rating given for the 3 terms by the students. The power of Friedman ANOVA. The power of the test is relative to the power efficiency of the parametric one-way ANOVA and the number of levels of the independent variable. The smaller the number of levels, poorer is the power efficiency. Using IBM SPSS for the Friedman ANOVA. Let us take a research example to explore the data for Friedman ANOVA using IBM SPSS 20. The problem chosen can be the same as taken in the Kruskal Wallis test in the previous section. However, the research question analyzed is different now. The independent variable of electric stimulation is operationally defined at 3 levels: the first treatment, removed treatment and the restored treatment. The dependent variable is the same, that is improvement in pain as measured by the McGill Pain Questionnaire. Each treatment is repeated for 6 weeks. After putting the obtained data on the data sheet, the following commands may be given to obtain a measure of Friedman's ANOVA. We may start as click Analyze, click Non-parametric tests, click on Legacy dialogues, click K-related samples, click over first treatment, removed treatment and restored treatment under test variable list, click on Friedman under test type. Click on the statistics button, check the descriptive box and then continue and then OK. After giving these commands, some results would be generated. You save the generated output as the Friedman results. Summary of the text. The non-adherence to parametric assumptions in data paves the way for usage of non-parametric statistical techniques in research. Analysis of variance is a highly robust test when its assumptions are met, but otherwise non-parametric alternatives like Kruskal Wallis and Friedman ANOVA have to be used. The Kruskal Wallis test is the non-parametric equivalent of the one-way ANOVA. The test aims to investigate if several independent samples chosen are from the same population. The test assumes that the underlying variable has a continuous distribution and requires an ordinal level of measurement. Some statisticians call Kruskal Wallis as the non-parametric ANOVA or ANOVA by ranks also. The Friedman ANOVA is used when the data from K-match samples are at least in ordinal scale. The null hypothesis tested is that the K samples have been drawn from the same population and the sample size is same as the samples have been matched. The power of non-parametric tests is given in terms of power efficiency of their parametric counterparts. If the assumptions of parametric ANOVA are met, then of course it is a powerful test. But if the assumptions of the parametric tests are not met, then Kruskal Wallis or Friedman ANOVA, they are much more powerful than their parametric equivalent. The text also discusses the IBM SPSS 20 commands to be used for Kruskal Wallis test and Friedman ANOVA. and they have been shown in the text.